My name is Christian Suppan, and I will be presenting neural screen space rendering of direct illumination. Modern rendering methods are able to produce images of incredible detail and accuracy. To do this, they require complete and precise scene descriptions, meshes, textures, light sources, participating media. Authoring these takes a lot of time and effort, which is fine for offline applications like movies. But what if we don't have access to all that data? What if we can only partially observe something because it is hard or dangerous to get to? What if we don't have time to build a complete scene model because the use case is interactive? What if the quality of the data isn't very good because it was generated by affordable sensors? One such case that immediately springs to mind is augmented reality. A solution is neural rendering. This is exactly what it sounds like. We replace traditional renderers with neural networks. This allows us to use all sorts of less complete inputs. We can use videos, drawn annotations, and all kinds of sensor data. Most neural renderers are image-to-image methods. They use videos or just multiple photos to create novel views of or relight their subjects. A plethora of methods exist in this domain. Prominent examples include Chen's neural texture-based approach, Sitzmann's deep voxel features, and Lombardi's warped volume Fourier matching. But irrespective of the intermediate representation, the output of an image-to-image method depends largely on the input images. Altering these in a way that achieves a specific result in the output takes skill and may be impractical depending on the size of the image set. These methods are limited in their ability to modify appearance. One related work that takes a different approach is called deep shading. This paper made two contributions. Firstly, they used deferred buffers to add a variety of rendering effects to existing images, but they also introduce real shading, a neural network-based approach for mapping deferred buffers to shading, also known as screen space rendering. Unlike methods with image input, deferred buffers offer much more direct control over the appearance of the output. However, this method is currently limited to untextured diffuse materials, and illumination is baked into instances of the network. That brings me to our contribution, the Neural Direct-illumination Renderer, a neural screen space renderer of which a single trained instance can render a variety of materials and lighting conditions. The NDR maps deferred buffers of depth, normal, roughness, diffuse albedo, specular albedo, and light encoded as spherical harmonic coefficients to a rendered image. The insight that allowed us to achieve this was to use the intrinsic image decomposition. Instead of trying to directly render the final image, we instead render shading maps and then combine them with albedos to produce the final image. This image formation model allows us to eliminate a known operation, the multiplication with albedo, from the learning task. Because albedo is separated from shading, our method is fundamentally limited to direct illumination only. This is what the system actually looks like. The NDR is a 2-encoder, 2-decoder unit that outputs diffuse and specular shading maps. Deferred buffers are processed by a convolutional encoder, while the light, expressed by a vector of spherical harmonic coefficients, is processed by a fully connected encoder and concatenated to the bottleneck. For exact structural details, please see the paper. Another key design feature is that we calculate coarse shading maps with very few samples based only on surface orientation as an additional input. These shading maps don't feature any shadowing or other occlusion-based effects, but they still help to sharpen up the shading and specular highlights in the final output. The buffers that the system requires as input can be extracted from real scenes with depth sensors and inverse rendering methods, but procuring these in a volume required for training a neural network is impractical. Instead, we use a synthetic dataset. Each training target is created by generating a number of geometric primitives. We distort these with random height maps, apply a random texture, and combine them into one or more objects by applying random translations and rotations. These are then rendered as ground truth using a path tracer, and the required input buffers can be extracted directly from that. Now, there are several things we can do to demonstrate the value of our contribution. Firstly, we can show that it solves the problem of limited data rendering, which is to say it produces plausible images and it does so in real time. Secondly, we understand why our method works. The use of intrinsic image decomposition and coarse shading input greatly improve the quality of the rendering. And lastly, it is an improvement over what came before. With regards to producing plausible renders, our method produces easily identifiable objects with sharp textures, shading, shadowing, specular highlights, and Fresnel effects. We can also show that the output varies believably and accurately when the input buffers are modified. We can confidently say that our method produces plausible renders, and it does so in real time. Our unoptimized research code runs at just over 21 frames per second, which is fast enough for interactive applications. We achieve plausible renders at interactive rates because of the design choices I have highlighted. As a reminder, the NDR predicts shading maps instead of the final render, and we calculate coarse shading as an additional input. This example clearly shows that without explicitly disentangling albedo, all textural detail is lost. Shading, including the specular highlight, is still indicated, but the render is no longer plausible. Without the coarse shading input, the highlight shape and location is also noticeably less accurate. We can therefore justify the performance of our method. Finally, we demonstrate that our method is an improvement over the state of the art. Existing work in neural screen space rendering is limited. The closest point of comparison is the previously introduced real shading, which produces diffuse shading with illumination baked into the network. Real shading produces visually similar diffuse shading, but lacks a specular component. We also compare to the general purpose image generator Pix2Pix. Without a specialized architecture, it fails to produce plausible shading. The lack of explicit separation of diffuse and specular shading also means that they are entangled for Pix2Pix. The bottom row should just be the sum of the top two rows, but Pix2Pix produces an exceedingly bright image. To illustrate that our method outperforms traditional rendering methods in a limited data environment, we also compare to the coarse shading input, which is equivalent to deferred shading without shadow volumes, as well as comparing to a ray-traced mesh constructed by offsetting vertices of a triangulated plane based on the input depth map. The shading input fails to produce plausible renders due to the lack of any and all occlusion-based effects. The mesh-based approach is extremely sensitive to noise in the depth map. Even for this synthetic object, a tiny numerical error has caused a noticeable artifact, which does not appear in any of the neural methods. Another failure case not shown here is that the mesh-based approach will not handle occlusions caused by unobserved geometry because no mesh has been constructed for it. It also takes on the order of seconds to minutes to complete the path tracing. Here we see a graph of the structural dissimilarity index of all of these methods over a dataset of diffuse objects under the same illuminant, which is suitable for evaluating real shading. The NDR outperforms the state-of-the-art real shading and all other methods. Also note the long tail of projection meshing caused by test cases where unobserved geometry contributes significantly to the final render. In addition to outperforming real shading numerically, our method also handles complex materials and varying illumination. For comparison, we use this textured phone under 3 different illuminants. As with the previous example, Pix2Pix is heavily artifacted and also exceedingly bright due to the entangled diffuse and specular shading. The coarse shading has erroneously bright regions due to a lack of shadowing, and while these examples look plausible, the same failure cases of the meshing approach still apply. Here we see a structural dissimilarity comparison for a dataset of fully textured objects under a variety of illuminants. The NDR again outperforms all other methods, and we again see the high variance of the path tracing approach in a limited data environment. Which brings us to the end of our evaluation. In conclusion, the Neural Direct-illumination Renderer achieves plausible screen space rendering at interactive rates with more controllable parameters than state-of-the-art by leveraging intrinsic image decomposition. In future, this method may be improved upon by incorporating real training data and handling subsequent bounces of light. Thank you for your time.